reference, I cannot get the reference. What we got here?
I just can't walk in the. You know what? I already did my
I
part.
write the rest of my
Did my
applications. I've applied to 2 and then I like look at the about it.
It's hard because it's so selective. It's like, I don't know.
Well, I think you will.
Before I do this, let me give you a thing here. And I didn't talk, I mentioned this probably in passing, I think. But I want to make sure that we all got it down here. So, any R module, and here I mean R is a ring of identity, unitary module. You assume it's commutative. M is the homomorphic image. A3 R module. You actually did this in your homework. It's one of the homework problems in the case where it was a finite generated, finite generated. But this is true more generally. And I want to show you what our pretty little diagram will do for us. So suppose well, actually, yeah, let Y and M be each other. So take a subset of the module that generates it as an R module. And if you're a lazy person that doesn't want to think critically, one thing that you could pick for Y is the whole dang thing. You can pick all of them. You know, it's certainly all of them generates M, right? But you might be able to find one more economical. So I'm going to leave you with that option. Let the cardinality of X equal the cardinality of Y. And let F be free on X. So take some other set X of the same cardinality of Y. Doesn't matter, just some abstract set. And let's suppose that X is let F be free on Xi. So I'm going to let these Xi be a basis of F. Remember, this is just an abstract element, so you can think of this in correspondence with, like, you know, some basis of the free module F. So here we've got our diagram. Include X into our basis of F because I'll let F be free on this. I just treat this as an abstract set. It just so an element of X is all possible finite sums of this. These are linearly independent because I put no relations on. Right? Everybody okay with that? And let this, I'm going to call this F, where F is bijection from X into Y, which I'm realizing is a subset of M. So just take, we know that X and Y are the same cardinality, so there's a bijection here. So take this bijection and just correspond it to the elements of Y as we had here. Now, along comes our hero, free module. This gives F bar. There's an R module homomorphism. F bar from free module on X into M. And it satisfies, when I do iota and F bar, it's the same thing as F. Right? Now, I've got most of my claim here done because I have at least a homomorphism from F into M. All I need to do is convince us all that this is onto. Well, anybody see why it's onto? Notice that if you look at F bar of iota X, this is
Close.
well, right. If you look at F bar of iota X, this is everybody agree with me? So what's generated by the image of X under this is what's generated by Y, which is all of them, because I assume that Y was a generating set. And this is, of course, and of course, this is, well, what we've shown is that M contains the image of F, right? Because the image of F, whatever it generates, has got to be inside of M. And so, since certainly F goes to M, this is an equality. And so, therefore, any R module is the homomorphic image of the free module. That's something that I promised you earlier. That's a big one. And I'm actually going to use it when I discuss projective and injective business. Okay, any questions? Yes.
Oh, so is it F bar that's onto?
Yes. In this particular setup, that F bar is onto.
Dr.
Mhm.
F is just a bijection, it's not necessarily a homomorphism.
No, it's a map of sets, right? In this particular case, it's a bijection because I picked the one that goes between X and Y.
Sure.
But actually, this diagram works no matter what. This is just a function of sets.
Sure.
And that's the old thing about all you have to do to tell what a linear transformation is tell what it does to its basis. The same principle is true for an R module. If you have a basis of it, if you tell that basis where to go, that determines the entire homomorphism. Okay. Oh, let's discuss the test. I forget about you guys. I've got your test is next Wednesday. Can everybody make that? You know, Wednesday, I'm gonna do Monday. I've got a Monday review session set up in Martin 102. Is that okay for y'all? Now, on the day of your exam, let's see, we're supposed to start at 9:05. I can get here and start you guys up. And we're supposed to be done at 9:55. There's a class that does come in here after us. They're probably gonna be more chill than people. So let's yeah, big class. I propose that we start the exam at 9 o'clock, and I'll give you because the next class after us is at 10:10, right? I'll give you from 9 to 10. Can anybody not make it by that time? If anybody's got an objection to going an hour, I'm not gonna out you, you can email me and let me know, and I won't reveal your name, but I'm gonna plan to do it from 9 to 10. And then I'll give you like a 7-minute grace period to upload it. You should take a picture of the PDF business and all that. Okay, so I think that's what I want. Everybody okay? Yes.
So, and the exam will be exclusively on the module period that we covered thus far,
Yeah.
up until Friday or up until Wednesday?
Oh, up until probably Monday, I guess. As opposed to what? What else are you worried about? I'm not gonna ask you political science questions or anything like that.
Okay.
I wouldn't know the answer anyway. So I am going to do this kind of as a dual projective and injective modules. They're kind of dual notions of so I'm gonna start with projective, one of my favorite. Definition. Consider the following diagram. Of our modules. With exact bottom row. So the exact bottom row business, all that means is the homomorphism from B to C is onto. So here's what needs to be projected. In a certain sense, you might think of B as sort of, in a certain sense, bigger than C, right? Because this is an onto map. Suppose that you have big guy mapping onto perhaps smaller guy here, and you have this R module homomorphism from P to C. You can lift that up to a homomorphism to the bigger guy. This is where it needs to be projected. We say E is projective. If there exists H from P to B such that doing G H is the same thing as doing F. And of course, what it needs to be projective is this works for any diagram, right? So as long as you have an onto map and some P here, you can always project it to the bigger one. That's what it means to be projective. I gave you all a definition in the homework for projective that is equivalent to this, and we're going to tie that together today. But I can't resist. So I gave you the definition from my notes for the other one.
Dr. Quinn?
Yes.
That's GH, not HT.
Did I do it wrong? HG. Yes, of course I did. That's why I do it. Algebra. Consider the diagram. Consider the dual definition. 12, 6, 2. Follow the diagram. With exact top row. And of course, exact top row in this case just means that the map F is 1 to 1. this is kind of the dual notion, right? Now, in this case, since this is one-to-one, in a loose sense of the word, you might think of A as a submodule of B. Right, this is one-to-one. And so what it's gonna mean to be injective is if you've got this R module homomorphism from G into I on this little piece of B, then you can lift it up to a homomorphism that starts on the big piece. Or all of it. We say I is injective. If there exists H from B to I such that we F, then you do H. That's what you got doing.
So for 12.6.1, G is on.
Yes, G is onto, so I'll emphasize that. And here F is one of that. Okay, so those are the two notions here. Okay. So I gave you this definition in the homework for injective. Projective, I gave you some free, and like I said, I'm gonna tie that together here. But notice how these are kind of the mirror images, right? You reverse the diagram, you reverse the direction of the maps. Projective modules are actually very important in homological biology. Yeah, I always think of projectives as I personally think of them as sort of more important than injectives, but that's not to take away from that. Injectives are sometimes a little bit harder to deal with. I'm going to point out something that if you have vector spaces, if you're over a field, then if you're over a field, then all of these things are equivalent, and they're equivalent to free. However, over, so say for example, over the integers, over a PID in general, if you have a projective module, in fact, it's free. And so you've got this large class of free modules. It turns out that any free module is projective, right? Injectives, frees are not injective over, say, in fact, free injective over Z has to be something called a divisible group. They're bigger and they're harder to build. And we'll talk about that a little bit. But the first, I'll get this one out of the way, and this is a big one. If you have I'll just state it briefly. A free module is always projective. You all did an example, I think in the homework, finding a module that was projective but not free, right? Did anybody come up with an example where the ring was an integral domain? I bet almost all of you use Z6, am I correct? There are examples over certain integral domains of projectives that aren't free, but they're harder to come up with it. Theorem 1263. Every free module is, and I'm going to prove this using just our current definition. It would be a cheat if I use the homework definition to do it at this point. So I'm going to do this right. Proof. Let F be free. Say X. So we'll say that X is our basis. Right? Capital X is the basis of that. and consider the diagram. And see what I'll call these maps here. Gmap. So let Moda next to F in the inclusion to basis in F. Now, I'm going to use the fact that the map here G is onto, and I'm going to do the following little bit. So if you look at F iota xi, so I'm just being fancy here. I'm taking one of the basis elements, xi. Iota puts it inside the free module, and then I apply F to it. I push this down here. There exists such that G of BI is equal to F iota xi. Right? And really what I'm doing here is I'm using the fact that this homomorphism here is on to. So no matter where this goes, there's something coming out of B that went to it. So this gives us a function. F star, and I do mean function here, from X to B. Right? And this function F star of xi is bi. Everybody okay so far? Not yes.
Just to, this is way further back, but when we say the F is free on X, what do we mean by that necessarily?
It just means you can interpret X as the basis. So for example, if you have your set X is xi, no matter how big this index is, then a typical element, if I mean F is free on X, is in form Ri1 xi1 plus Rik xik with no relations. So if you have no relations on this, then the xi is the abstract set is a linearly independent set. Right. So just think of X as a basis. Okay. So F induces an R-mod homomorphism call it H from F to B. So here's our H. And notice that, and of course, this must behave the same way this does. But so H iota xi should equal F star. xi. Which equals, of course, bi. So, we can wrap this up now. So if you look at G H iota xi. Then this is equal to, G of bi. And G of bi is F iota xi. Everybody okay with that? And so let me point out that F and GH agree on iota xi for all I in the index set. Therefore, F is equal to GH. Because the iota xi's are the basis of the free module. GH and F agree on all the basis elements, so it's got to be the same on the ones. Yes.
How do we know F star is well defined? Because couldn't there be multiple BI for?
No, we made that. We made a choice here, right? So, yeah. So what we did is, you're right. We're doing the action of choice here. Technically, the way I did this, because for every element xi, I projected that down here and pulled it back here, and there's a lot of choices, right? And maybe I had to make a whole bunch of them. Therefore, F. Okay. Any questions so far? Okay, so I want to do a little bit of preliminary stuff with injective. So that's a big takeaway here is, okay, anything that's free is projective. Injective's a little bit, I'm not going to dive too deeply in this class into this. I'm going to skim over some of it, but I'm going to give you kind of some of the highlights. I'm going to only prove one direction of this. First thing, definition. Let D be an abelian. How many of you have ever heard of a divisible group before? Well, here we go. We'll say that this group is divisible. If we're all in the natural numbers, and D and D, there exists D prime and D such that N D prime is equal to. So this is why it's called divisible, one might argue. What this says is, given any element of D and any positive integer N, D over N is still in the group. That's essentially what's going on here. Can anybody think of an example of a divisible group? Yes.
Cyclic groups.
I think actually, I don't think any such cyclic groups, actually. Right, because take if you take something like the integers.
Yeah.
Right? Just take 2.
Mhm.
Not every integer is divisible by 2. Right? And if it's finite, you've also got problems if it divides the order of the group. Kind of. Come on, you can think rationally. Yeah, that's right. Cute. How about cube the reals? Right. In fact, any abelian group things cube. Oh, here's one for you. Can you think of a divisible abelian group in which every element has finite order? This is kind of treated way, right? Because every element of Q or R, other than 0, has infinite order. Anybody think of finite? So I want a divisible abelian group, and every element in it has finite order. Was that I would love the smart aleck answer. Absolutely correct. Let me rephrase the question. So checkmate, you got me. Can anybody think of a non-zero divisible group in which every element has finite order? Here's one that here's one that topologists are fond of. Q mod Z. Right. So this is the set. So think of it this way. This is sometimes called the rationals mod 1 because every coset. So take any rational number, right? If the rational number is 0, then well, if the rational number is an integer, let's say 7 plus 0, whatever, that's equivalent to 0 plus, right? So you can take a representative in the interval from 0 to 1, right? On the other hand, if the rational is not an integer, you can basically write it down on your calculator, and if it's positive, you could just jerk off what's to the left of the decimal point and have just that decimal, which is between 0 and 1. And if it's a negative, you could just add integers into it until you get something between 0 and 1. This is why this is sometimes called the rationals mod 1, because every one of those cosets has a representative that lies between 0 and 1, including 0, not including 1. Everybody agree with that? And the addition is mod 1. 1/2 plus 1/2 is 0, right? And 2/3 plus 2/3 is 1/3, right? Because it's 4/3 and it's wrapped around. You can think of it as sort of putting the interval 0 to 1 on a circle and kind of keep going around and around. Notice that every element is of finite order, isn't it? Because if you have the coset A over B, if you add that to itself B times, you will get 0. Agreed? So there's got that. So everything in here, this is what we call a torsion group, because everything in it here is finite order. Even though the group itself is infinite, everything's finite order. Why is it divisible? Well, that's actually not too bad, right? Because if I want to divide this coset AB plus Z by N, I'd just be A over BN, right? Do I agree with that? And so if you take A over BN and multiply by N, you will get A over B, right? So there's a good example of a divisible group that is torsion. Let me give you the following lemma, which I may use the sequel, but I'm not going to completely prove. I'm going to prove one direction of it. And this might seem a little limiting, but it's the seeds for what starts, so. Unlike the previous theorem about projectives, I'm gonna specialize to Z modules here. Lemma, 12.6.5. D is a divisible abelian group. If and only if D is a divisible, injective Z module. So this is kind of a nifty thing here where we show that the notion of divisibility is equivalent to injectivity for a Z module. I'm going to do one direction. I'll do that direction. So we know that D is injective. We want to show that it's a divisible group. So what I want to do here is so I'm going to follow the definition here. When we take an element D out of D and an arbitrary natural number, I want to show that somehow I can divide D by N and stay in the group. So I want to consider the following diagram. So this is inclusion. Of course, what I mean by this is the ideal generated by N, or the submodule, if you will, generated by N. So this is NZ. This is inclusion here. And I guess I should probably talk about F a little bit. Oh, right. And script about F here. And F from NZ and D is given by F of NK equals N. Or I'm sorry, no, it's not KD. There we go. So in other words, this is just the function that takes N into, just takes N. And you know, I'll tell you, you can go ahead and verify that this is an R module homomorphism if you want, but I'll tell you kind of a slick way to think about this. NZ is a free Z module, right? It's free on N, right? Yes, it is a proper submodule of Z, but that doesn't matter. It's isomorphic to Z. It's free on N. N is the basis element here. And what am I doing? Essentially, I'm taking the basis element to D. So this, I don't expect this map to be onto, but what it will do is it's taking that basis element N and it's going to the arbitrary element D and just seeing what it generates. And because it's free, this is automatically a good old-fashioned all-American homomorphism. So this works out here, right? Now, this gives us an H. If I call this inclusion, since D is injective, there exists H from Z into D such that when I do O to H, it's the same thing as doing F. And so, now to finish this off, let D prime be H of one. So just see where one is the generator here, just see where it goes down here. And notice that if you look at ND prime, which is H of N. Now, of course, N goes to N here, and this should be F of N, which is D. So N D prime equals D, therefore D is this. The proof that divisible implies injective is a little bit more involved. This is one of the subtleties about injective. It turns out that you might complain about this for good reason. Say, well, Jim, you're just really restricting yourself to Z modules here. What about more general ring? There is an analog of this notion of divisible and more rings, and you actually use a divisible group to start off with, and you build something a little bit more general to make the equivalence injective there. But that's more weeds than I want to get into here, unless anybody wants to come see me in my office or whatever. We can talk at length until you regret having come by. All right, so I want to give you two theorems here in parallel because I like the way these kind of pan out here.
How do you get from ND prime to NH prime?
ND prime.
Oh, you just replaced it.
Oh, I just defined this.
Oh, okay.
Yeah. Any others? Okay. So here are my parallel theorems. And I just really dig this. I'm going to call this theorem 1266 P and the other one, theorem 1266I. So projectives and injectives kind of dual motion, so you see this kind of parallel theorem.
You beat Euclid?
What's that?
You beat Euclid? You showed the parallel postulates here?
No, I don't plan to do that. Let P be our module. The following are also let I be an R module. Follow. For this one, A, P is projective. B, every short exact sequence of the form 0, A, B, P splits. Number C, there exists an R module. K. And a free module. Free R module F, such that, P sum K is isomorphic to F. This last one's very useful, and it's a characterization I gave you in homework. What it means to be projective is it's the direct summand of a free. And from that particular perspective, if that's your definition, it makes it obvious that any free is projective. We'll say more on it. There's a dual notion here. A, I is injective. B, every short exact sequence of the form 0 I B C 0 splits, and C I is a direct summand of any R module that contains it. So if I is a submodule of some module, it has to be a direct summand of that module. Yeah, maybe write that down a little more explicit. So I is contained in A implies that A right. Okay. Any questions on it?
When you say splitting, I know it's like the direct sum, but like what part is the split? Like, is it when
Right.
it goes to the?
So if this sequence actually splits, it means that there is a homomorphism that goes backwards, that this composition is the identity on P. And equivalently, that means there's a homomorphism that goes backwards here, such that this composition is the identity on A, right? So this is F, G, K, H, then see when I do H, G, it's the identity on P, and when I do F, K, it's the identity on A. So, and sometimes those backward arrow red ones are called the splitting, right?
Okay.
Yes.
But then B is also the direct sum of A and B.
Yes, but it's not equivalent, right? So whenever the exact sequence splits, whenever you have a split exact sequence, the middle guy is the direct sum of the bookends, right? But just because the middle guy is the direct sum of the bookends does not necessarily mean that the sequence splits. The example is not easy to find, really, but it's not equivalent.
But that also doesn't mean that B is always a free module.
What's that now?
Because if you consider B to be the direct sum of the bookends, that doesn't mean that B is also free. Like, we're not saying the same thing.
No. I mean, for B to be free, these would at least have to be projective, right? So for example, if you have, so you could have a split exact sequence, Z2 sum Z2, and Z2. And as Z modules, none of those are even projective, right? Or injective. They're nothing. They're garbagey. Which I'm not sure is a real word. Okay, any questions? Any questions? All right, well, I will see you folks next time. Is everybody good with the 5 o'clock on